beautiful to watch dancing northern and southern lights across the night sky in north and south poles. These lights are generally known as aurora borealis or aurora australis. So, let us study where does this light come from. It all starts from the sun. The sun is 150 million kilometers away, but still it affects on Earth. During solar storm, solar flare and solar wind sends out charged particles. These charged particles travel away from the sun with high speed. When this charged particle reach the Earth's atmosphere, this charged particle gets trapped in the Earth's magnetic field. The magnetic field causes them to move in helical path along the magnetic field lines. And so they are channeled towards the poles due to magnetic force. These molecules collide with atoms and molecules of the atmosphere and emit light. The motion of the charged particles in the magnetic field results in such an eye-catching phenomenon. So, we saw that the helical path of the charged particles in the magnetic field is the result of such a phenomenon. So, let us study in detail about the motion of the charged particle in the magnetic field and how the helical path comes into play. So, the magnetic force acting on a charged particle moving with velocity v is given as F is equals to q v cross b. Since magnetic force is given as the cross product of velocity vector and magnetic field vector, force is always perpendicular to the velocity as well as the magnetic field vector. Since it is perpendicular to the velocity vector, there is no work done and so there is no change in the speed of the particle. But since there is a change in the velocity vector, there is change in the direction of the path of the particle. Let us consider a simple case where velocity vector of the particle entering the magnetic field is perpendicular to the magnetic field. So as you can see, I'll make the parallel component of velocity vector to be 0, making the velocity vector perpendicular to the direction of magnetic field. And if I increase the perpendicular component, the magnitude of velocity vector increases. So here, as you can see, that the particle follows a curved path and the curved path increases till it completes a circle. So as you can see, the curved path is continuing till it completes a circle. So let us go in detail of the situation. So if you observe carefully this situation, the magnetic force is towards the center of the circle. This means that the magnetic force acts as a centripetal force. Thus, magnetic force acts as a centripetal force and so Fb, that is the magnetic force, is equal to centripetal force Fc, which is equal to mv square by r, where v is the velocity of the particle and r is the radius of curvature of the circular path followed by the particle. Since Fb is nothing but qvb, we get the radius of curvature to be equal to mv by qb. This gives the radius of curvature of the circular path. This also implies that larger the momentum, more is the radius of curvature of the particle. The time period of the charged particle is the time taken by the charged particle to complete the circle. This is given as t is equals to 2 pi r by b, which comes out to be 2 pi m by qb. Let us now consider another case where velocity vector has a component in the direction of magnetic field. Now let us take some parallel component of velocity vector, that is, velocity vector having some component in the direction of magnetic field. So as you can observe, velocity vector and magnetic field vector are making some angle which is not equal to 90 degree. Now here, you already have learned that the perpendicular component of the velocity vector is responsible for the circular path. Right now, we also have some parallel component which results in the constant motion along the magnetic field. So let us see what is the path of the particle. So as you can observe, the parallel and the perpendicular component of the velocity vector results into helix path of the particle. So the perpendicular component gives a circular path and the parallel component gives the motion along the magnetic field, that is a linear motion. So let us study different terminologies related to the helix path. So as you can see, this is similar to what we observed now, and the perpendicular component results into circular motion and the parallel component results into linear motion. Here, the radius and the time period remain same as we observe for the circular motion, and the radius r is equals to mv by qb is nothing but the radius of the helix. Let us now calculate the distance moved along the magnetic field direction. So, the distance traveled by the particle in the magnetic field direction in one rotation is known as pitch, and it is given as p is equals to v parallel component into time period. So, this is known as the pitch of the helix. This helical motion of the particle is similar to what we observed in aurora borealis. So you got to know that how the motion of the charged particle in magnetic field gives such a phenomena what we observed as aurora borealis. And so in solar flare, when charged particles like protons and electrons are ejected from sun gets trapped in Earth's magnetic field, this particle move in helical path in presence of Earth's magnetic field. Magnetic field lines come closer to each other near the magnetic poles, and so the density of charge is greater at poles. This particle collide with atoms and molecules of atmosphere, and excited oxygen atoms emit green light and nitrogen atoms emit pink light. Thus, the helical path with light gives this effect. In the next topic, we will learn about motion in magnetic field as well as electric field. So, we will meet there and we will see what is the path of the particle. And we will also learn about working of particle accelerator and working of one of the particle accelerator, that is cyclotron.